Good afternoon. Thanks for coming. I had a clever introduction prepared, but I can't really compete with that, so I'll just dive in. I am going to talk about how to use T-digests as generative models to do single-pass algorithms for data science. The basic landscape of the talk is I'm going to talk about features and what it means to do feature randomization, and then I'm going to segue into 3 applications in data science that use feature randomization as a component. And then I'm going to take a digression into discussing kind of like what T-digests are and how you can use them to do generative random sampling. And then with that knowledge, I'm going to go back to those 3 applications and reprise them and show how you can do them all in a single pass easily using T-digests in this mode of operation. And then I'll just conclude with a little demo. So they say you should start at the beginning. I'm going to start way at the beginning. This is a feature vector. It's an ordered list of numbers, which all represent measurable properties of some object that you're interested in. They form the input to model training algorithms to produce models, so like this little net down at the bottom. And then they also, of course, form the inputs to those models to produce predictions. So here on the left, there is a data set, and each of those rows represents a short feature vector. And so the operation of feature randomization is to independently randomize the values in each feature column. This preserves the distribution of each individual feature, but it erases all the information about the relationship between features. So a statistician would say it preserves the marginals, but destroys the joint distribution. There's a couple different ways you can do this. The first one here is you can do permutation. So permutation is useful if you want to do randomization without replacement. One of the properties of it, of course, is the size of your output is governed by the size of your input, as you can see on the left there. A second method is selection, where you just generate essentially like random indexes into the column and select values. Here, it's nice because you can generate outputs of any length you want for your purposes. It does produce values with replacement, as you can see, that little yellow box on the right. I'm going to be focusing for the rest of the talk on selection randomization because it works better for these kinds of algorithms. The three particular algorithms I'm going to talk about today were all either directly due to or inspired by Leo Bremen. Right around 2001, he introduced the idea of random forests, which are, of course, an ensemble of decision tree models. Each tree is trained on a random subset of data, and then each split considers some random subset of the features. So the first algorithm is random forest clustering, and this proceeds. The first step is you start with some feature data, as on the left, and it has some joint distribution. I just did a simple 2-dimensional set so that I could kind of make this clear in a slide. You then do random, selection, feature randomization to produce a set that has, of course, the same marginal distributions, but you've lost the information on the joint. So these light pink points on the right are this new synthetic random sampled data sets. So once you have this kind of a data set, what you do is you train a random forest model to learn these real points from the fake random sampled points. Now out comes some decision trees on the right, which know how to do this. I like to think of this as kind of like inducing your learning model to learn the location of your feature data in the larger feature space, because that's really what it does to learn this problem. And so how you apply this is income on the left, your actual feature vectors. You feed them through your random forest model, and you keep track of what leaf node each vector lands at for each tree. And you collect those leaf node IDs into a vector like the one on the right here. And the basic trick for random forest clustering is you cluster on that right-hand side in the leaf node space. Now, if you've ever used this technique, this is basically just a reminder, and unfortunately, if you've never used it, it's probably more like just a teaser, but I'm going to move on and if you need to learn more about that, I encourage you to contact me or drill down on your own. So another closely related technique is you can use this idea for feature reduction. This proceeds exactly the same as before in the first two steps. You start with some feature data, you generate the synthetic randomized data, train your model, but instead of trying to cluster anything, all you do is you take a look at what features your random forest model actually used. And you use that as a reduced dimensionality feature set to do a feature learning. The last algorithm I'm going to discuss is also due to Brayman, and it's called feature importance. And so his idea was, if you have some feature data and you want to figure out what the importance of one feature is, you can take your data, randomize just that one feature, run it through your model, and then compare the change in accuracy between doing that and just taking the correct data. And so you're essentially measuring directly the impact of that feature, because you're essentially taking away the information and saying, well, if it was important, then I'm going to see a big change in model performance. And so his idea is, well, I can do that for every single feature in my data set and get a profile for every single feature as to how important it was to my model. What's nice about this is any predictive model can use this technique, and it's very functional. In other words, you don't have to care at all about like the interior structure of whatever that learning model is. All you're saying is, if I randomize a feature and it has a big impact on the performance, it's important. So in the prehistoric world, before MapReduce, most data, either fit directly in RAM, or at the very least, it fit in a single file on your, machine. But of course, in the modern world, we have things like, MapReduce, and in particular, of course, Apache Spark, where your data lives in multiple partitions and quite possibly across, many individual machines. And so in this case, it's much less clear how you can do randomized selection on each individual column when your data is like not living all in the same place and are in the same data structure. So I'm going to put a pin in that for a minute and talk a little bit about T-digests. T-digests are a sketching data structure introduced in this paper here, written by Ted Dunning and Omar Erdl, and there's a link to that paper there. There are several implementations of this. There's implementations in Java, Python, R, JavaScript, C++. I created a Scala implementation not too long ago. I also have, since my last talk, actually got user-defined aggregator functions produced for this in Spark and PySpark. So what kind of a sketch is this thing? It takes in a stream of numbers. In our case, we're interested in streams of numbers that are, feature columns. And it generates a sketch of the cumulative distribution function. And so just to briefly review, if you have some x value in your number space, it's going to tell you the probability of the number being less than or equal to that. And you can see they're, of course, monotonic for that reason. They have some great properties. The first one is they do incremental updates. So if you have a t-digest, you can dump in another value, and what you get is an updated t-digest. That's a very efficient operation. This makes them great for taking sketches of very large data sets or streaming data that's unbounded. You can just keep a very compact running sketch of your data as it passes by the t-digest. The second hugely important property of these things is that you can also aggregate them. So if you have data in Spark, of course, it's sitting in different partitions. You can take a t-digest sketch of each partition in parallel, and when you're done, you can aggregate them to get a final t-digest result. So this, of course, is your classic, scale-out parallelism model. Another trick you can do with these things, and this is the trick I'll be leveraging today, is you can do what's called inverse transform sampling, which sounds fancy, but all it means is you generate a random number uniformly from 0 to 1, and you find a value x such that the CDF of x is equal to that number. And what this allows you to do is just randomly generate values that are effectively taken from the distribution represented by the sketch. And of course, that is the representation of the distribution of your feature data if you've trained one of these things up on your feature columns. And so now we have a way to do generative sampling from a really compact sketch of your data. So what does this mean? This means that inverse transform sampling is a replacement for random selection directly from your feature columns. That means we have a way to, say, broadcast in Spark a collection of these very compact T-digest sketches and use them locally to generate entire partitions full of data, which is effectively the same as if we had directly sampled from the feature vectors. So now we no longer care that it resides in different partitions. We now have a single pass way to train a sketch, and we have a single pass way of using that sketch to generate the synthetic data that we want. So in RF clustering and feature reduction, this looks exactly like you'd expect. Instead of doing the direct selection from the columns, we take our sketch and do generative sampling, and we get exactly the same kind of result as we would have if we just done a naive sampling. The feature importance is a bit trickier because, of course, conceptually what you really want to do is generate an entire copy of your feature data for each single feature, just one column randomized. And so that's obviously very time and space inefficient. It's logistically difficult, and even worse if you're trying to do this in a partitioned, data environment. So what can we do to fix that? You start by loading in a single feature vector from your data, and you run it through your predictive model, and you get, of course, an answer. And this is your reference answer. This is kind of like the answer you get under normal operation. If we're looking at like the jth feature we're studying, we take that value and we just save it off to the side for a moment. We replace it with, a generative random sample from the corresponding sketch we took of that feature. So now it's just some random value that has the same underlying distribution. Now we run that feature through our learning model, and we get some different answer. And we take that and we compare that answer to the reference, and we measure a deviation. You can see here I just basically took the absolute deviation, which is a pretty good measure for, say, a regression model. And one thing that's nice about this technique is you can easily configure what deviation measure you're using for either regression models or classification models. So it's a very flexible method. And you take a running sum of these things for each feature. And then when we're done, we advance to the next one and we do the same thing over again. So essentially doing an evaluation for each one of our features as we run through this one single row of our RDD or our data set. And so when we're all done, if we move all the way down all the data in our feature data, when we're done, we have a cumulative deviations saved in a vector corresponding to each of our features. And then all that's really left is to divide by the size of our data, and we define that as our feature importance for each feature. Now, since all these things are nothing but running sums, they also aggregate very easily. You start with your feature data. You do what I just described for the feature vectors in each different partition. And of course, since they're nothing but sums, at the end you can aggregate them perfectly easily and then divide by n and you have your importances. So if you add all that up, what we have is one pass feature importance. It's linear in samples and features. It's not just linear, but it happens in a single pass over your feature data, and even better than that, it parallelizes across all your data partitions. And so really we have the map reduce scale out hat trick, and it's the perfect fit for doing fast operations in a tool like a Spark. So the data set I use for the upcoming demo I'm going to do is the TOX21 data. If you saw one of my previous talks, you have already seen this data set. It was commissioned by the NIH in 2014, and it was essentially data on 12 toxicity assays for compounds, candidate drug compounds. And they collected 800 dense features on each of these compounds. And there was about 12,000 training samples and 650 they held out to use as a standard testing set. And the particular format of the data I took from Johannes Kepler University in Linz, which the link to that particular set is down below. And so now we're going to move on to the demo. This is a live demo, so hilarity may ensue. Just got a notebook going on here. We begin with the usual imports for Spark ML and data frames. We input some Seaborn plotting routines. Here we're going to import the actual code, the package that we use to do these feature importance computations that I just talked about. This is a library you can import to use in your own notebooks from Maven Central, and it works for both standard Spark and PySpark. And we load the data up. And so as I mentioned before, there were 12 toxicity assays. Here are the names of them, and if you are a toxicity chemist, you might know what those mean, but I surely do not. And they are labeled subsets for each assay. Not all the assays had the same examples labeled, so you can kind of look at what that looks like. You can see there's just NAs for different ones, and it's not all the same. And this first snapshot makes it look a little worse than it actually is, because in fact, about 2/3 of the samples were labeled. You can see it's right around 8,000 out of 12 for each one, but they're not. They're all different. So I have to convert the 800 columns that I loaded in using a vector assembler, which is a great little Spark feature. Now they're Spark ML feature vectors, and I create a little function whose purpose is nothing but to filter out the NA values for each particular data set, and I'm kind of creating 10 sub-data sets. And so here's where things finally start to get interesting. I now have 12 data sets, one for each of my toxicity assays, and through the magic of Python list comprehensions, I can actually train 12 individual toxicity models at once. Because this is running on my laptop, that takes a short but measurable amount of time. So I want to stress, I guess, while it's grinding through this, that we actually now have 12 learning models, and I'm going to explain why that's kind of a good demo in a second. So now that we have this, I can do, as I described before, a single pass over my feature data and fit a T-digest sketch for every one of those 800 features. And I configured that to hopefully run relatively fast. It's already done, so now I have a sketch for each feature. And here, I'm going to finally do some feature important computations. And I'm going to talk a little bit about what's going on here. You can see, first of all, these are pipelines. And you can tell that because it has a transform method, and it has parameters. One of the parameters, in this case, actually happens to be a learning model. And so I'm running through each of those 12 toxicity models I just described, setting it as the parameter and saying, okay, I want you to compute the feature importance for this model, and then when I'm done, I want you to compute the next one, so for all 12 of those. So it's doing a lot of work, but it's doing it in one pass over the data, and it's doing it parallelized by partition, and so you can effectively make this run as fast as you want to just by getting enough partitions and throwing enough threads at it. Also what I'm doing is at the end doing a little sort, and I'll show you why that matters. It looks like it's finished. Excellent. So if I look at one of these things, here's the output of a single feature importance run, and of course basically on the left it has a feature name and the importance value calculated. And I sorted these in descending order of importance, so these are the top 20 importance values you're seeing here. You can see that the numbers aren't very large to begin with, but they drop off in magnitude very rapidly. So if I extract those values into pandas format data frames for Seaborn, because Seaborn likes that, and I can do plots. And so I take the corresponding plot of that distribution, we see that it's a classic Zipfian. Most of the values are at or near 0, and then there's a little tail off to the right of values that had higher importances. So you might ask, are they all like that? And of course, because we have that data, we can basically plot a similar plot. I used a violin plot just to be more compact, but you can see that they have different dynamic ranges, but they all have the same shape. They have a big blob near 0 and a tail rising up to the top of higher values. And this is what makes feature importance computations useful. You can do things like, say, I'm going to take the top 10% of those and use them as a reduced feature set. You can take the top 20 of them and look at them, because if you're a practitioner on your data, you of course have domain knowledge, and it's going to tell you a lot about like what the models actually thought was important when you trained them. So with that, all that's really left is to talk about ways you can drill down and learn more if you're interested. Yesterday, my friend and colleague Will Benton gave a nice talk on building machine learning algorithms on Apache Spark. And if you're interested in like the logic of creating your own scale-out algorithms that you can do efficient aggregation on, that's another place, a good talk to view when they post it up on YouTube. I gave a talk on, last February on sketching with T-Digest. If you want to learn more about the details of how T-Digests work, you could go see that talk. And in June, I did a application of also T-Digest to random forest feature reduction. So if you're interested in how feature reduction works, as I described earlier, you can learn about that. The random forest clustering I discussed is available as a package you can download from Maven Central. As I mentioned earlier, the T-Digests and the feature importance work are available in a different package. So those are 2 links there. And lastly, I have the notebook for this talk that I just showed you up on GitHub as well. And so when they post these slides, all of these items are links you can follow. And that was all I had to talk about. Happy to have any questions.
Thank you, Erik, for the wonderful talk. We've got about, thank you. We have about 7 minutes, 7.5 to be more precise. There are 2 mics at the end of the aisle. I would request that if you have any questions, please walk up to it, because we want to capture those questions in the audio. Go ahead.
For T-Digest to work, does it assume anything about the distribution of the variable?
No, it doesn't. That's actually one of its excellent properties. It'll really faithfully sketch pretty much any shape of distribution.
Does it work for discrete, like for instance, categories of 10 things, which you could do also maybe CDF of? But
I like your question. Yeah, the library that I have does do discrete values. You can configure it to just directly store counts up to some basically threshold number of unique values, and if you see more than that, it'll start kind of treating it like it's numeric. So if you know you've got a lot of binary data or categorical data, you just set that parameter and say, I want you to do discrete distributions.
Any more questions? Well, if none, then give a big hand to Erik for sharing T-Digest with us.